at 9:14 a.m. On October 14, 1943, on a runway still covered in thin morning fog in eastern England, a B-17 Flying Fortress rolled back to its base in a condition that, by every aviation engineering standard of the time, should not have remained airborne for more than a few dozen seconds. The nose of the aircraft had been torn open. Most of the cockpit glazing was shattered. Engine number 3 had been dead for more than 40 minutes. One flap was jammed at an abnormal angle. Along the right side of the fuselage, more than 100 holes from flak and fighter fire overlapped each other. The auxiliary electrical system was gone. Hydraulic pressure hovered at the bare minimum. And yet the aircraft landed, stayed aligned, did not slide off the runway. And, most importantly, 9 men stepped out of it alive. According to U.S. Army Air Force's training doctrine, a heavy bomber that lost an engine at combat altitude, suffered severe structural damage to the nose and wing, and experienced degraded flight controls, had almost no chance of returning to base. Aerodynamic models of the period showed that a loss of just a few additional percentage points of lift, or a slight shift in center of gravity, would send a B-17 into an unrecoverable loss of control. But that morning, the aircraft appeared over the field anyway, slow, heavy, as if dragging behind it the full weight of assumptions that had just been proven wrong. There was no cheering, no ceremony, only the quiet attention of men who understood they were looking at an outcome that did not fit any chart, table, or doctrine they had been taught. The mission that day was a daylight bombing raid against the ball-bearing factories at Schweinfurt, Germany. It was a target of high strategic value and one of the most heavily defended areas in Europe. The flight path from England to central Germany forced B-17 formations to spend hundreds of kilometers over enemy-controlled airspace, where German fighter coverage and anti-aircraft artillery were layered by depth rather than concentrated at a single point. At altitudes above 25,000 feet, thin air reduced the effectiveness of both engines and control surfaces. Outside temperatures routinely dropped below -30 degrees Celsius, making metal more brittle, thickening lubricants, and slowing human reaction times. Every control input required greater physical effort, while the margin for error became smaller. The B-17 was designed to operate in tight box formations. Individual survival depended less on maneuverability and more on overlapping defensive fire. Once an aircraft fell out of formation, it became an isolated target, easier for fighters to attack and harder to protect. On the bomb run, the formation had to fly straight and level for several minutes to ensure bombing accuracy. That same stability allowed flak batteries on the ground to calculate firing solutions with precision. A single shell detonating close enough could cause severe damage through shrapnel and blast pressure alone. That morning, B-17 serial number 42 to 30,390 was hit by flak just after leaving the target area, as it began its turn away from the most heavily defended zone. The aircraft commander was Captain Robert Bob Caldwell, 27 years old, from a working-class family in Indiana. Before the war, he worked in an agricultural machinery plant. The job taught him nothing about flying, but it taught him how systems fail under real loads, and how to keep them running when they no longer behave as designed. His co-pilot, First Lieutenant Thomas Reed, had studied basic mechanical engineering before enlisting. He was accustomed to noticing small changes, vibration, sound, resistance, that signaled deeper problems. To Reed, machines always spoke before they broke, if someone paid attention. Flight Engineer Staff Sergeant Frank Miller grew up in an auto repair household. He understood fuel systems, electrical systems, and, most critically, the relationship between weight distribution and controllability. On a B-17, Miller was not just a gauge reader. He was the crew's practical problem solver when theory stopped applying. The remaining crew members, navigator, bombardier, gunners, were ordinary men in the most literal sense. None were trained to do the impossible. They were trained to follow procedures, maintain formation, and execute tasks on schedule. War rarely allowed all three at once. Before this mission, Caldwell's crew had completed 8 combat sorties. They were not exceptional. What they had was familiarity with each other and trust built under pressure. The B-17 Flying Fortress was built on redundancy. For engines, primary and backup electrical systems, redundant hydraulics, reinforced airframe sections. In theory, it was an aircraft designed to absorb punishment and keep flying. But that design relied on assumptions. Damage would be dispersed, not concentrated. Control surfaces would remain functional. Forces would stay roughly symmetrical. Losing one engine could be managed. Hydraulic failure had procedures, but no checklist addressed the simultaneous loss of an engine, severe nose damage, and degraded control authority. Systems worked when failures were isolated. They failed when multiple assumptions collapsed at once. After the flak burst, 3 core design assumptions no longer held.
Moments after leaving the target, engine number 3 lost power and stopped. Almost simultaneously, flak tore through the nose, shattering cockpit glazing and depressurizing the aircraft. Hydraulic pressure dropped toward warning levels. Caldwell faced 2 options. Option A: order an immediate bailout. At that altitude and temperature, over enemy territory, survival odds were poor, but doctrine recommended it when control was compromised. Option B: attempt to keep the aircraft flying, leave formation, and head back toward England. This violated safety guidance and exposed the aircraft to fighter attack, but offered a chance for everyone to survive. Caldwell chose the second option. Not out of bravado, but because he judged the aircraft still controllable. Barely. That decision eliminated all safer alternatives, but because he judged the aircraft still controllable. Barely. That decision eliminated all safer alternatives. With engine 3 dead, asymmetric thrust became the first problem. Caldwell and Reed adjusted power on the remaining engines gradually, avoiding sudden increases that could overstress them. Speed had to be maintained without amplifying yaw. Miller recalculated fuel distribution. Fuel in the dead engine's wing became dead weight. He began transferring fuel incrementally to reduce asymmetric moments, careful not to shift the center of gravity too abruptly. Altitude control followed. Caldwell lowered the nose slightly to maintain minimum controllable airspeed, trading altitude for control authority. Descending meant denser air and better control, but also increased exposure. When German fighters appeared, Caldwell avoided aggressive maneuvers. The gunners fired short, controlled bursts. The goal was deterrence, not kills, to minimize airframe stress. A jammed right side flap created persistent roll tendency. Reed held continuous corrective input, straining his arm. Caldwell adjusted speed, and Miller continued fuel trimming to ease the imbalance. Communication remained minimal. Only information that altered decisions was spoken. Approach and landing presented the final risk. With limited hydraulics, Caldwell carried higher than normal airspeed on final, accepting a longer landing roll. He avoided a full flare, letting the aircraft settle onto the runway with minimal pitch change. The aircraft touched down hard but aligned. Once rolling, aerodynamic forces no longer threatened structural failure. The aircraft did not need to fly anymore. It only needed to stop. When the engines shut down, exhaustion set in. Several crew members suffered mild frostbite. One gunner had a scalp laceration from shattered glass. Reed temporarily lost sensation in his arm from sustained control input. Inspection revealed damage beyond normal repair thresholds. Structural members were bent. Electrical systems burned out. Engine 3 was a total loss. There was no celebration. Only the recognition that survival hinged on the after-action report listed damage and control decisions. Doctrine remained unchanged. Systems do not rewrite themselves for rare exceptions. Still, among engineers and aircrews, the incident became a quiet reference point. Data was analyzed. Fuel distribution and asymmetric control effects were discussed. The aircraft was dismantled. The crew returned to duty after rest. No special commendations followed. Days later, a young technician stood beneath the dismantled wing, marking damage points for documentation. The mission was logged as completed. The aircraft no longer existed, The crew flew again in other aircraft. No manuals were rewritten that day. But for those who sat in that cockpit, the meaning of limits had changed. They understood that sometimes systems stop answering, and only a chain of small, disciplined decisions keeps something that should not fly in the air.